Hello. In the previous lecture, we have looked at the importance of one-dimensional cavities. In this lecture, we are going to figure out what should be the design of the mirrors in order to uh, create, for example, a stable cavity. So the stability of light, that would mean that if I put in radiation within such a cavity, we also call it a resonator. In a stable cavity, the radiation would remain within the cavity as the light continues to bounce back and forth. Whereas in an unstable cavity, the light would walk away or walk off from the cavity after a certain number of passes through it. So to get to the stability, I'm going to employ a method which is basically based on ray diagrams, okay, or ray optics. Now, all of you have studied ray optics from very early on, and we have used, for example, ray optics in understanding image formation using lenses, mirrors. We are going to use a similar set of principles, but we are going to describe the ray in a mathematical fashion. Not just that, it is important to understand that ray optics is actually an approximation to the actual field, to the actual description of field propagation. Ray optics is the limit wherein you don't care about the wavelength scale that is associated with the electromagnetic wave and take the limit that lambda tends to zero. In that limit, ray optics is a valid approximation. And to me, it is also very nice and interesting that a simple analysis based on ray optics actually gives you the stability of a field, of the full field within the cavity. So let us begin. So imagine I have two plane mirrors and I want to confine light within for with such geometry of the mirrors. Now you can clearly see that alignment is extremely critical for such a design. Particularly, even a small angle between the mirrors, right, can lead to the light being essentially, walking off from the cavity. So you see that alignment is critical when one comes to using planar mirrors for creating a cavity. Similarly, one can see that if I come up with a cavity in which both the mirrors are uh, convex, certainly this is not going to work, right? This is going to be an unstable cavity because only the fields which are precisely along that are going to work out, whereas any field which is comes at a small angle from the axis of the cavity is going to walk away. So what we are looking for is the notion of stability. So what we do is to get to stability, we will construct something called an ABCD matrix associated with ray propagation. So my light, for example, is traveling in a certain direction, right? This is my ray of light, and there is a certain axis. This is the optic axis of my system. This could be axis of symmetry about which mirrors are arranged. It could be axis about which a lens is placed, and so on and so forth. So you see, a ray can be uniquely identified with two numbers. What are the two numbers? So this is my z direction. So if I'm looking at a point here and I'm trying to identify this ray, I associate the ray with two numbers. One is the lateral displacement. Let me call it r as a function of z. The lateral displacement of a ray could be there, or it could be a ray which is there. So you see that the lateral displacement, so this amount of displacement, this quantity is what I'm calling as R of Z, which could be different for different rays. So the second quantity with which I require two numbers to specify it, the second quantity is basically the slope of the ray, right? Which I'm writing it as R prime of Z, or in other words, it is simply dr over dz, right? So you see that this ray, the red ray here, I'm associating with r and r prime at z, which gives me the slope, right? This angle theta is what is given by the slope with respect to the z-axis. Similarly, the green ray has got a r prime of z, which I associated with it. So you see that these are the two quantities that are sufficient for me to uh, uniquely characterize the ray. Now, what I'm making here is a very important approximation called a paraxial approximation. By paraxial approximation, what I mean is that my r prime of z, which is dr over dz, is essentially tan theta, where theta is the angle with respect to the z-axis, which approximately is equal to sine theta, which for small angles of theta is actually theta. So in the paraxial approximation, I'm going to deal with this small angle approximation. All my rays, if any, are moving more or less parallel or to within, let's say, 20 degrees of the optic axis. That is what is called as the paraxial approximation. The other assumptions, so I'm writing the assumptions again in green. So the first assumption I wrote down was paraxial approximation. The second assumption which I'm writing down is that the there is cylindrical symmetry in all that which I am going to consider. That is, if I am putting in lenses or mirror about this optic axis, there is cylindrical symmetry about the whole problem. So I'm going to limit my discussion to spherical circularly symmetric lenses instead of something like a cylindrical lens, right? So I will avoid those and assume all through cylindrical symmetry in my discussions. So given that these are the assumptions made, now let us go ahead and first get a feeling for these two numbers. So R is clearly telling you this radial distance from the optic axis, lateral displacement, okay? Because it's cylindrical symmetry, when it's talking about a radial displacement from the axis, it is not from a point, but from an axis. The second important thing is that if R prime of Z is positive, right? That would mean that as Z increases, right, displacement increases. Similarly, if it is negative, which would imply that as Z increases, the displacement decreases. Right. So now let's look at various physical situations So the first situation which I want to talk about is free space propagation. Free space propagation, what you have, again, the geometry is clear. I will draw the geometry here. Let's say this is my z-axis and I'm looking at a particular ray which has been characterized. So I am looking at a location z1 and I'm asking free space propagation from z1 to z2, right? So the question I'm asking is what happens to the ray as I propagate from z1 to z2? So you can clearly see that my displacement, later displacement at z2 can be written as the later displacement at z1 plus I can write down r prime, which is calculated at z1, times the distance between the two, which is z2 minus z1. Clearly you will see that this will give me, so if this point is r at z1, we are talking about this point which is r at z2, right? Similarly, one can ask what has happened to r prime at z2, and we will realize that r prime of z2 has continued to remain as at r prime at z1. That is, for free space propagation, I can capture this transformation between r and r prime in terms of a 2 by 2 matrix equation. And this 2 by 2 matrix that characterizes, uh, for example, free space is what we are calling as the ABCD matrix, which contains 4 elements, which is a 2 cross 2 matrix. So for free space, I can write down my R final and R prime final, right, in terms of R initial and R prime initial. F and I represent initial and final. And you can clearly see that given this above equation, right, with this, I can identify the 4 elements. So the elements are 1, and this is z2 minus z1. There is 0, and there is 1. So you see this on matrix multiplication is equivalent to the above equation. This ABCD matrix characterizes the free space propagation. Now let us undertake the same exercise for a lens so that we can derive the lens, and I am at the moment looking at a positive or a converging lens. A mere change of sign will give you the negative lens, but then let us just look at it here. So again, what do I have? In a similar manner, the previous, I have my symmetric z-axis. I'm looking at a lens and I'm looking at a thin lens approximation, right? The the size of my thickness of my lens is negligible. Okay, this distance is negligible, right? So what do I have? If I come in with a ray of light in that direction, then what happens is that my lens essentially changes the direction of the incoming ray, and I get a initial Ri prime which is positive, it changes my RF prime beyond the lens to be negative, right? So one is clearly going to, when I'm measuring this angle, this is my positive angle, whereas if I, that is, I'm measuring the angle from the Z axis, and in this case, I'm going to measure this angle, which is a negative angle, right? So now let's see how we can deal with this. The the location of the ray at the location of the lens, I'm calling this distance, I'm calling this as Ri, which by the way, you can clearly see is equal to Rf. We have taken the thin lens approximation, right? Negligible, and this is what I'm calling is as thin lens approximation. And within the thin lens approximation, my Ri, all that the lens does is to change the direction of the ray without changing its displacement between the initial and the final ray. Right. So we again write down the two equations. I can write down my Rf as same as Ri. That is a simple part. And then I can write down my Rf prime, which is the change, is simply Ri prime minus Ri by F. So let us figure out how we got this. So in my diagram, I have this point as my object, and this point is what I have is the image, and we know the object image relationship, that is 1 over u naught. You have seen the lens equation. I'm going to simply use that 1 over u naught plus 1 over v, where u object and v image are the distances of the object and the image, is actually given by 1 over f u naught, and this distance is vi theta naught, which is this angle, and theta image is that angle. My theta naught is Ri by u naught. Similarly, my theta I, this is a negative quantity, is Ri by v image now. And recall that we have in the paraxial approximation. So you say theta naught indeed by definition now is same as Ri prime. Theta I, which is for the image, is simply Rf prime, right? These are our two relationships. I put back these in the lens formula. So what I have now is Ri prime. I put these back into the lens formula. So the lens formula is what I'm rewriting in terms of these quantities. So you see, I can write down 1 by u naught as simply Ri prime by Ri minus, because remember that this is negative, I need to have my slope is negative, right? So this is my minus Rf prime by Ri, which is equal to 1 over F. This essentially gives you our second equation, which is that Rf prime equals to, right? So this is how we get this second equation, and this allows us to now get back and write down the ABCD matrix associated with the lens. My ABCD matrix relates the input and output of a lens. So across a lens, what happens is the lens does not affect the lateral position, right, which is Ri and Ri prime. All that it does is to affect the slope of the input ray, and this is the ABCD matrix, right? These four terms are the ABCD matrix associated with a lens. This is how a lens transforms the input ray to an output ray. One can do a similar exercise, right, for a mirror, which is what is important for us. So I am just rederiving this step by step so that you can repeat these calculations for yourself. So for a mirror, again, I come up with a similar diagram. So what I have is my Z axis, and for the mirror, I'm exaggerating, what I'm looking at is a convex mirror at the moment. And then for the mirror, there is a radius of curvature R, right? And you see that if I come in with, again, so I come in with a ray, so radius of curvature is the radii. So this point gives you the center of the sphere of whose part the concave mirror is made of. So if I come in with a ray like that, the angle of incidence is going to be equal to the angle of, these angles are going to be in the same, right? So you see that I can I can now look at this whole thing in, let me call this angles as alpha, let me call this central angle as beta, and let me call this angle as gamma, right? So I can now rewrite the relationships for these. Now clearly you know the following, that this is this displacement is Ri. So across the mirror you see that Rf is same as Ri. Again, what the mirror does is to uh, change the direction. So now you see, if I'm looking at Rf prime in my setup, you see that this angle is precisely minus times gamma, right? This is my Rf prime. This is the uh, angle associated with the final ray, whereas the incoming ray is simply Ri prime, which is equal to alpha, correct? This is the slope of the incoming ray, and this is the slope of the outgoing ray, which is a negative number. Here I am looking at alpha, beta, gamma as positive numbers, so that there is no confusion. And you can clearly see that these angles can all be related. For example, I know that beta plus theta is going to give me gamma, which is like the sum of the uh, so now I'm writing down the relationship between the internal angles and external angles in this diagram. You can clearly see that the the external angle is equal to the sum of the internal angles. So I can write down beta plus theta. Similarly, I can write down that gamma equals beta plus theta, right? In other words, it can also be written as alpha plus 2 theta, so that I can write down my theta as gamma minus alpha by 2. So let me now do these equations one by one. I can write down, let's take the first equation, which is Rf prime is minus gamma. So I can write down Rf prime, which is minus gamma, which is equal to alpha minus 2 beta. You can clearly see that from here. So you see that my 2 beta is same as 2 alpha plus 2 theta, which is simply 2 alpha plus gamma, which I can rewrite as, remember that alpha is essentially the Ri prime, right? Whereas beta can be written as minus 2 times Ri divided by R. Remember, Ri by R is going to give you essentially beta. And again, I am looking at thin mirror when I'm claiming that this distance and that distance both are R. The curvature is very small, and this also ensures that one is in the paraxial approximation, which will again make all these angles as small angles. All right, so given now the equation number one and this second equation, I can write down the ABCD matrix that characterizes a mirror. So what I have is RF, that there is little change in the displacement, whereas this can be written as minus 2 over R, where R is the radius of curvature of the lens, and that is the relationship between, that is the ABCD matrix for a mirror. Now you see clearly that R by 2 essentially behaves like the focal length of a mirror, where R is the radius of curvature of the mirror. Right. So now that we have got, operationally these few matrices, what the ABCD matrix does is to actually allow you to do the following. I'm interested in looking at a propagation of field of the ray across multiple length elements. So imagine this. Imagine I have something convex. This is F1, this is F2, and then I have maybe a mirror. So I can break down this complicated problem into steps. That is, so I can ask what happens at the point X, point Y, point Z. So between X to Y, I have got free space propagation. At Y, I have got a lens, positive lens, followed by another free space propagation, another lens, and again followed by a free space propagation and followed by a mirror. So you see all of these quantities will simply involve my initial ray, this is my R initial, R initial prime, the ray at which it is coming in. I have got, this is the free space propagation matrix from X to Y, followed by another the ABCD matrix for the lengths at Y, followed by another free space propagation matrix from Y to Z, again followed by the lengths at Z, and so on and so forth. I hope you get the point. So this is how, after I multiply all these matrices, what I can do is to basically obtain at the end of it the final ray, its location as well as its slope. Both of these quantities would be arrived at by looking at this transformation that takes the ray from point X all the way to the final point here. So you see, this is the power of this business of ABCD matrix that allows you to incorporate now and play around with the locations, and this is widely used in lens design and so on, and it's an extremely powerful idea that is widely utilized.